Hi, everyone, and welcome to our second lecture video of the day, all about the structure of metal alloys. By the end of this lecture video, you will be able to represent a metallic solid and/or alloy by showing a model that shows the essential characteristics of these types of compounds. So to get us started, it's important for us to be able to distinguish what's different and special about metallic bonding. Here, in metallic bonding, electrons are delocalized, which means delocalized, D means not, localized means local, right? So delocalized means that electrons are being shared throughout all of our different metals, and we call this kind of a sea of different electrons. So our metallic bonds, by that definition, means that the bonds lack directionality, which makes metals have a lot of different properties of being malleable. We're able to manipulate metals because they don't have bonds that are super structured. They lack directionality. And because electrons can easily move throughout, that makes them high thermal and electrical conductors. And if you think about wires and computers and different electric systems, they're all made up of different metals because metals are really good conductors of electricity because electrons are able to move freely throughout. So if we take a peek kind of on the atomic level of metallic bonding, we have our positively charged ions here. We know that our metals form positive ions, and when they lose the electrons kind of move freely all throughout our different metals that are present. They kind of form this bigger concept of an electron cloud and within that, there's kind of a sea of electrons where electrons can move in and out between different ions, and ultimately that makes them great conductors of electricity. Thinking about the structure of that metallic bonding, our neighboring metal atoms join together in what we call a metallic lattice. So from our last lecture video, we talked about ionic lattice structures. We can extend that now to metallic lattice structures. Lattice is just that 3D structure of how our different compounds or structures look. And extending metallic bonding a little bit further, we can have what we call alloys. And alloys you've probably interacted with on a daily, regular basis. It's a combination of two or more metallic elements. And there's two different types of alloys, substitutional and interstitial, which we are going to spend the rest of the video talking about. But alloys are when we have different mixtures of different types of metals blended all together into one specific lattice. So an example here of our substitutional alloy is shown here, and how that might visually be different than our interstitial alloy, but let's spend a little bit of time talking about each. Substitutional alloys are when atoms of our different metals have similar atomic radii. So if we take a peek here between tin and copper, they have a relatively similar size. So if we had an alloy, which means it's a mixture of copper and tin, because they're the same size, they retain a similar lattice structure that can kind of stack right next to each other and not really fit in the crevices of our lattice, which ultimately makes them remain to be malleable, meaning they can be movable or changed. And ultimately, they have a similar density. The reason they have a similar density is because the atoms are spaced out similarly across the whole alloy. A couple of examples of this, if any of you have jewelry made out of sterling silver is a lot of silver with a couple copper metal atoms spread throughout. And because silver and copper have similar sizes, this is a substitutional alloy, which is why sterling silver is good for jewelry, because people can manipulate it to make necklaces or earrings or other types of jewelry as well. Comparing substitutional alloys to interstitial alloys, these are alloys that have different atomic radii. So what we see here, if we have an alloy of carbon and iron, in this case, carbon is kind of special. So carbon can kind of behave sometimes as a metal. So in this alloy where we have iron and carbon together, carbon is a lot smaller than iron. So ultimately what happens is we have our iron structure here, and the carbon is able to fit into the little crevices. It's basically playing a game of hide and go seek, and carbon is really good at that because it's really small. So they're ultimately able to fit into these little crevices that happen because iron is a lot bigger than it. If we look at it kind of on a 1 level 2D scale, we see ultimately that the carbons are able to fit into these little gaps that are caused between ions being next to each other. And ultimately, that makes our alloys really rigid and ultimately changes the physical properties. Interstitial alloys are really solid. So some common interstitial elements are really small atoms like hydrogen, bromine, carbon, nitrogen, oxygen, and silicon. And some common examples of this are a lot of steels, stainless steels, which hold up bridges. The reason stainless steel is used is because it's super solid. It's really rigid. It's not going to break or move around, right? And that's good for building structures because they have to be rigid to withstand gravity, pressure, all of the different building requirements. But interstitial alloys specifically is a mixture of having different metals of different sized atomic radii. So that is the end of this lecture video, and I will see you in class. Bye, everyone.